Hello, today we will continue learning about propositional logic. We will focus on truth functions. What is a truth functional proposition? It is a compound proposition that uses one of the five logical operators and whose truth value can be determined solely on the basis of the truth value of its components. In other words, the truth value of a truth functional compound proposition is determined by the truth values of its components and by the logical operators involved. Now, I will present some definitions that are important for propositional logic. What is a statement variable? It is a variable that can stand for any statement, simple or compound. We use lowercase letters such as P, Q, R, and S. In propositional logic, a statement form is an arrangement of logical operators and statement variables such that a uniform substitution of statements for the variables results in a statement. An argument form is an arrangement of logical operators and statement variables such that a uniform substitution of statements for the variables results in an argument. A substitution instance of a statement occurs when a uniform substitution of statements for the variables results in a statement. A substitution instance of an argument occurs when a uniform substitution of statements for the variables results in an argument. Now, what is a truth table? It is an arrangement of truth values for a truth functional compound proposition that displays for every possible case how the truth value of the proposition is determined by the truth values of its simple components. Now we will study the truth table definition for each one of the logical operators. Let's begin with negation. Since negation simply changes the truth value of the statement that follows it, the truth table definition is easy to construct. Here we have it. The leftmost P is the guide for the truth table. It lists the truth values for a statement variable. In this example, P stands for any statement that can be either true or false. The tilde changes the value of the statement that follows it. Therefore, if P is true, as in the first row, then its negation tilde P is false. You can think of negation as somewhat like the minus sign in arithmetic. It changes the value of what follows. In the second row, the truth value of P is false. Therefore, the truth value of its negation is true. The construction of truth tables for the four remaining logical operators will be a little different than for negation, because each of them has two components. For example, the logical form for conjunction P.Q has two statement variables, P and Q, each of which can be either true or false, two truth values. This means that the truth table will have to display 4 lines. So here we have the truth table for a conjunction. P stands for the first conjunct, Q stands for the second conjunct. In the first row, we have that the truth value of the two conjuncts is true, so the conjunction on the right column is true. And then in the other rows, whenever there is a conjunct that is false, the conjunction is false, as it is shown on the third column to the right. In the last row, if both conjuncts are false, the conjunction is false. The truth table definition for this junction also has 4 lines. You can find it on this slide. The truth table definition for this junction, the wedge, shows that a disjunction is false when both disjuncts are false. That is what it is shown on the last row of the truth table. Otherwise, it is true. Therefore, a disjunction is true when one disjunct is true or when both are true, as it is shown in the first, second, and third row of the truth table. As mentioned earlier in the chapter, this interpretation of the word or and the definition of the logical operator uses inclusive disjunction. Here are a few examples. 1. Memorial Day is the last Monday of May, or Mount Rushmore is in South Dakota. 2. Either June or August has 31 days. 3. Either triangles have 4 sides or squares have 3 sides. In example 1, the compound statement is true because both disjuncts are true. That will be the case of the first row of the truth table. In example 2, the first disjunct is false, but the compound statement is true because the second disjunct is true. That will be the case of the third row of the truth table. In example 3, since both disjuncts are false, the compound statement is false. That is the case of the fourth row of the truth table. The truth table definition of the conditional also has 4 lines. You can read the truth table on this slide. The truth table definition for the conditional, the horseshoe, shows that a conditional is false when the antecedent is true and the consequent is false. That is what you find on the second row of the truth table. Otherwise, it is true. The first 2 lines of the truth table seem to fit our normal expectations. For example, suppose a friend is giving you directions to Los Angeles. She tells you the following: if you drive south on I-15, then you will get to Los Angeles. Let P stand for you drive south on I-15, and Q stands for you will get to Los Angeles. If you drive south on I-15 and you get to Los Angeles, the instruction is correct. That is reflected in the first row of the truth table, in which the conditional is true. Now let's imagine that you drive south on I-15, so P is true, but you do not get to Los Angeles. Then Q is false. In that case, the instruction is false, is incorrect, and that is what is shown on the second row of the truth table. Now, let's imagine that you do not follow this instruction. You do not drive south on I-15, so P is false. But through another route, you get to Los Angeles. In that case, since you didn't follow the instruction continues to be true. That is what is reflected on the third row of the truth table. Now let's imagine that you do not drive south on I-15, so P is false, and you do not get to Los Angeles. In this case, the instruction continues to be true, continues to be correct, because you didn't follow it. So that is what is shown on the fourth row of the truth table. The truth table definition for the biconditional also has 4 lines. You can read it on this slide. According to the truth table, a biconditional as the main operator is true when both components have the same truth value, either both true or both false, as in the first row of the truth table and the fourth row of the truth table. Otherwise, it is false, as in the second and third rows of the truth table. This result can be understood if we recall that the triple bar symbol for the biconditional is a shorthand way of writing the conjunction of 2 conditionals. So in the case of the second row, P is true and Q is false. Therefore, the first conditional is false, and since one of the conjuncts is false, the conjunction is false. In the case of the third row of the truth table of the biconditional, P is false and Q is true. So now let's examine the second conditional. Since Q is true, the antecedent is true, and P is false, that conditional, the second one, is false. And since one of the conjuncts is false, then that conjunction is false, and that is why the third row of the truth table of the biconditional is false. That was all for today. Remember to complete exercises 2, 8, and 15 of exercises 7C1, exercises 2, 8, and 15 of exercises 7C2-1, and exercises 2, 8, and 15 of exercises 7-2-2. Submit your answer on Brightspace by tonight at midnight. Have a good rest of the day.